Okay, good, thanks. Right, so this talk is going to be a little bit different to other talks we've had in this series. It's going to be a little bit more computational and have a little bit of a different flavour, but it's definitely about statistical scalability, so I hope it'll be a little bit interesting. So I'm going to start off by saying a little bit about what we mean by compositionality in the context of statistical modelling and computation. Why I think that category theory, a rather abstract area of pure mathematics, is actually very well suited to helping us think about compositionality in computing generally, in computation generally, but in particular in the context of statistics. What that has to do with functional programming, and why I think functional programming languages are also very well suited to thinking about scalable statistical computation. Basically how we can bring these two ideas together in order to make our computation more scalable. And in order to make it not too horrendously abstract, I will try and give a few little examples of composable algorithms mainly, and talk a little bit about composable models and what that means and how it all fits together. So we'll just have to see how far I get with the clock there. That's good. Right, so typically, when we're doing trying to solve a big problem, right, in statistics, but even more generally than that, how do we solve the big problem? Well, one way or another, we typically break down the big problem into smaller problems, and this has a long history in statistical computation. It's often called the divide and conquer approach. Somehow, at some level, you need to do that to solve any big problem, right? You might do it in a rather trivial way if your problem is in some sense big but trivial. But in more complex settings, it might not be obvious how to actually do this. And in fact, the challenge of thinking about how to take your big problem and break it down into smaller problems might be actually one of the key challenges to understanding the scalability of that algorithm. Okay. So I'm going to make this slightly brash claim that statistical models and algorithms are not normally formulated in a composable way. I wouldn't necessarily defend that statement to the death, but I think as a general statement is true. There are notable exceptions. So for example, in Bayesian statistics, which is where I work, things like Bayesian hierarchical models, they are really very naturally described in a very hierarchical, composable way. So that would be a good example of an exception to this rule. But very often they're not, right? Very often we'll just say, right, there's this huge matrix here, and there's this other huge matrix here, and you need to do these computations. And I'm not telling you how to break down that huge operation into a more easily manageable chunk. Okay, so in general, I think it's probably fair to say we don't really think about expressing our ideas in a composable way. So what's this got to do with category theory? Well, in some sense, category theory is the mathematical study of composition. If you had to kind of give a one-line description of what category theory is, I think that would probably be roughly what most people would say. And so that is the sense in which it's relevant to this problem. Okay. So I have a general sort of beef with the way we think about algorithms, and it's not even just about programming languages, it's the whole kind of way we think in this very imperative kind of Turing machine type way about what it even means to do computation, what it even means to think about what an algorithm is. And maybe functional programming languages help us turn that on its head and think about computation itself in a slightly different way, and I would argue a slightly better way, a slightly more compositional way, a slightly more scalable way. I'll give an example of that in a second. It's always a hard sell with statisticians, right? So with statisticians, I'd like to say, okay, you should think about things differently because it's better, it's more elegant, right? But statisticians are pretty hard-nosed, and they say, now, show me the money, right? So statisticians say, what are the concrete advantages I get from thinking this way? And one, okay, so I think there are lots of benefits of thinking this way, but one kind of really concrete thing that I just point at and say, look, this is something you will get for thinking about things in this different way, is it becomes completely trivial to parallelize and often to distribute all of your algorithms, okay? So back in the day, I used to write MCMC codes in C and other languages. I would spend ages writing and debugging a serial code, and then if it didn't go fast enough, I would spend ages rewriting it to try and make it parallel to run on a cluster or even just multiple cores, and it would be very difficult, very time consuming, very error prone, okay? Now I write all of my algorithms in parallel all the time. There's zero extra effort in me making my algorithms parallel, right? So that's a real tangible benefit. And they're easier to write, they're less error prone, easier to debug, okay? And you get them parallel for free. So there are loads of benefits from switching to this slightly different way of thinking. Okay, so even if you're not a big programmer, I would argue that it's helpful to just think differently. So here, this isn't in any particular programming language, but this is how people think about algorithms and talk about algorithms and put algorithms in papers. And what I would argue is this is an absolutely terrible way to think about computation or to describe computation, but this is what people do. So on the left here, we've got a simple algorithm for doing a trivial Monte Carlo sum. On the right-hand side, we've got a trivial algorithm for running a absolutely trivial Markov chain Monte Carlo simulation, right? They're both trivial, and it doesn't really matter whether you know what they do or not. That's not my point. My point is here that the way they're described, it's do this, do that, put this into this box, override what's in this box with that box, go back to this part of the loop, right? That's a really very imperative way of thinking about computation, and it's a really bad way to think about computation, because actually just looking at the descriptions of those algorithms, it's not at all obvious that the one on the left is trivially parallelizable and the one on the right isn't. Okay? So from a functional programming perspective, they're both folds, but the one on the left is obviously a fold that can be trivially transformed into a map reduce. Okay? So this algorithm on the left here is a fold map, and the algorithm on the right is a fold left. Okay? And so it's trivial that a fold map parallelizes and a fold left doesn't. There's
Are you going to define this term?
Yeah. As we go along.
I also don't know quite sure what you mean by an imperative code.
Very instructional, do this, do that, right? Rather than thinking about how you would compute something as opposed to what you want to compute. Yeah. So well, you'll see examples as we go along. But this is making sense. It's not completely obvious when you look at that list of statements, that one of these is trivially parallelizable and one is not, I suspect, right? They're both threading through a state, but in one case it's kind of trivial, and in the other case it's not. All right. So what's functional programming then? Well, in functional programming, there are lots of things that encourage you to structure your computations in a different way, right? If you try really hard, you can write code in a sort of imperative style, but it really encourages you not to, because it emphasizes immutable data, okay? So what do I mean by immutable data? Well, you can't change it. So once you've got, you can give names to things, like I can call this x, I can say x is 3, that's fine. But once I've said x is 3, that's it, x is 3. I can't then later say, I now want x to be 4, yeah? You can't do that, okay? So data is immutable, data in data structures is immutable. We use pure functions, so what we mean by that is that it's a mathematical function, right? It's a function in the mathematical sense. Very often in programming, our functions are not functions in the mathematical sense. So a function in the mathematical sense means if I give it the same arguments, I will always get the same results back. There won't be any kind of other funny things happening in the background. I will be writing to disk, I will be reading to disk, I will be printing to the screen, okay? It's a pure function. I give it my input, I get my output. In principle, I could paste the copy of that function in my code, and it wouldn't change the semantics. In principle, I could cache or memoize the results of that function. It wouldn't change the semantics of my code. Yeah, so it's just a mathematical way of thinking about computation and organizing computation. And so if you think in terms of something like early models of computation, the kind of whole Church-Turing thesis said that basically a Turing machine had the same computational power as the lambda calculus. Well, our imperative ways of thinking and programming that almost everybody uses are very much at the kind of Turing end of that spectrum, and these functional programming languages are very much at the Church sort of lambda calculus end of this spectrum. And what I'm arguing is that these more functional ways of thinking are much more compositional and much more scalable. Now, there's this whole separate issue about whether or not you have types. In general, I think types are a good thing, but it's not really the main focus of this talk. Okay. And there are lots of languages. So I'm going to use a language called Scala that I quite like to illustrate some of these ideas, but that's not really the point at all. It's really all about functional programming. Okay, so in pure FP, everything's immutable. Functions are pure and referentially transparent. They can't have side effects, right? You can't have global variables getting mutated in the background, etc. However, functions can be recursive, okay? So that can be a way of kind of getting around the fact that you can't have conventional sort of for or while loops in a pure FP language because you can't mutate a counter. Yeah. So, but recursion is a way of getting around that. But functions are nearly always first-class objects in these languages. They're higher order. This is an issue we're going to come back later. When we start talking about probabilistic programming languages, we actually like probabilistic programming languages to be higher order as well. What that means is you can pass functions into functions and you can get functions back from functions. That's totally fine, totally natural, and again can be used to make your algorithms much, much neater and cleaner, because in some sense you can send computation to your data rather than sort of sending your data to the computation. So that makes lots of algorithms much more natural. Okay, so the kind of the sell on this, the kind of the show me your money bit, is that this leads to lots of advantages. So what I said that it allows you to parallelize your code trivially. So why is that? Well, if you've ever done any parallel programming, you will know that actually the main problem with parallel programming is this issue of shared mutable state. You've got multiple threads running in parallel, and if you're accessing the same data, even if you're trying to read it at the same time as it's being written, or you're reading at the wrong time, you can get out of sync with reading and writing mutable data. Two threads can try and write to it at the same time. There's all kinds of things that go wrong, but almost all of the problems, almost all of the things that make it hard are to do with shared mutable state. But I've just told you that in pure FP languages you don't have any mutable state, so you don't have any shared mutable state, and so almost all of the problems just immediately disappear. I mean, that's not to say there are never any problems, that's certainly not the case, but 99% of the problems associated with writing parallel code just disappear in FP. Okay, and this is really the reason why there's been a recent resurgence in FP languages.
So this is overall an old idea?
Oh yeah. So FP languages have been around, I wouldn't say since the very start, but almost since the start.
Where are you taking the start from?
Of modern computers. In fact, even before that, right? So lambda calculus was before modern computers. So.
That's from the 30s.
Yeah, exactly. Okay, so some examples. Like I said, I'm going to use Scala notation to illustrate some of the ideas, just because it's useful to have some concrete notation, but again, that's not really the point. But the point is that we can use higher order functions to accomplish things nicely and elegantly. So suppose we have some data, again, it's a huge data collection, right? Think scalability, and we can say, oh, I want to map a function over that. Okay, so what does this mean? It means I want to double each element in this collection. Okay, and I'm going to get a new collection back. So map is a higher order function because it takes a function as an argument. Okay, so that's fine. In fact, any type, like list here, that has one of these map operations, in fact we call a functor. Again, this comes from category theory, we'll see the connection in a while. But that's all it means, it has a map method. Then there's another higher order function that many collections support called flat map. And what that does is a map followed by a flattening. Okay? So if we have something like a data structure and we map a higher order function that itself returns a collection, okay, then if we just map that, we get back a list of lists. Okay? And sometimes that's what we want. But very often when we have this kind of structure, actually what we want is the result of flattening this operation. Yeah? So if you have some kind of parameterized type like list here, which has one of these flat map operations, or just conceptually is a functor that can be flattened, then that's what we mean by a monad. Okay, and monads are like a really key idea in modern functional programming. There's lots of mystery surrounding them because they're quite an advanced concept from category theory, but actually in practice they're trivial. Right? In practice they're just something that can be flat mapped. Okay, so it's not a very mysterious concept at all. It's just that the mathematical theory that describes where these mathematical objects come from is quite abstract. So why are monads useful? It's because they allow you to compose monadic functions. So if we think about composing functions, and again, this isn't the way we normally think about computation necessarily if we're used to imperative programming. We might think about doing this to a variable, then doing that to a variable, then doing another to a variable. But if you really think about what's happening, You're just composing a bunch of functions together, and then you're threading a value through that composed set of functions. And really, all programs are just a function, right? They have an input, they give you an output. It's a function, and that function is composed of lots of other functions. So programming and computation is really about composing functions. So if you've got functions where the types all line up nicely, so you've got an F from S to T, a G from T to U, and H from U to V, you can just compose them together. And so in Scala, you'd write something like H compose G compose F. And that will give you the composed function. Or even if you didn't have this notation, you could write it yourself as a function that takes S to F of to H of G of F of S. Yeah. So that's going to give us your composed function that maps S to V. Okay. But monadic functions don't compose like that. So if you've got what I mean by a monadic function is one of these functions that starts with a raw type and gives you back a type wrapped in a monad. Okay, so at the moment we're thinking that this monad is represented by a collection. Okay, these don't compose together because if we've got an F from S to M of T and a G from T to M of U, we can't compose those together. They don't compose together because we'll end up with an M of T, but this function doesn't take an M of T, it takes a T. Okay, but we've just seen that flat map is the way to compose these things together. Okay. So they don't compose directly, but they do using flat map. So we can say F of S, flat map G, flat map H, right? And that then allows us to compose together those monadic functions. And this is such a common operation, this chaining together of monadic functions, that many languages have special notation for this. So in Scala, it's called a for expression. In other languages, it's called a for comprehension. It's actually called do notation in Haskell. And you write something that sort of looks imperative. It looks like you're saying, I want to take a T out of F of S, and I want to take a U out of G of T, and a V out of H of U, and then yield the result. Okay, it looks kind of the way you'd write an imperative nested for loop, but that's not what you're doing at all. This is just pure sugar, pure syntax for this chaining together of flat map calls. Okay, but to be able to do this, you have to have this flat map. Okay, so this is what monads give you. They give you this ability chain together monadic functions, and this turns out to be an incredibly common pattern in functional programming. Okay, but monads aren't just about data sets, they aren't just about collections, and so this is one of the reasons why people find them a hard concept, because they are very abstract. They can represent anything with a sort of flattening structure, and so for example you could use it to represent mathematical objects like probability distributions. So the probability monad we'll come back to later is just a mathematical concept, right? It's a concept that represents a probability distribution. So a rand T is something that represents a random quantity of type T, okay? So you can use this in order to kind of make your programs pure. And if you think about what map means, okay, what does map mean on a random quantity? Well, it's just a transformation. I mean, if the function is, for example, a monotonic function, you think of this as being a change of variable, right? So map is used to transform one quantity to another. Or again, if you kind of measure theory background, think push forward measure, okay? You're pushing forward the measure from one type to another type, okay? So that's what map does. And flat map is a way of chaining together stochastic functions. Okay? So if we've got a marginal distribution and we've got one of those monadic functions and S goes to T, what we're doing is we're marginalizing out the uncertainty in the source type to just get the uncertainty in the destination type. Okay? And so this is a way of thinking about these two things together, is a way of thinking about propagating uncertainty through a computational pipeline. So you can think of this in the context of uncertainty quantification, for example. And these probability monads, okay, both conceptually and in practice, can be used as the basis for understanding probabilistic programming languages. And again, I'm going to come back to this later. So to start with, I want to think just in terms of concrete things like messing about with data, but it's important to kind of flag up the idea early on that these monads aren't just about collections of data. They're about wrapping some context around the type and using that context and kind of embedding the semantics of that context into these higher order functions like map and flat map. Okay, but again, what are the practical benefits of this? Well, we can put the semantics of parallelisation into these monads. Okay, so conceptually, it's pretty clear. If we've got a collection of data and we're going to map a pure function over it, that can be done in parallel, right? There's nothing that, you know, one element depends on all of the other elements, okay? So if you've got a collection of n elements and you want to map it, okay, if you did that sequentially, that would be an order n operation. But on infinite parallel hardware, there's no reason why this shouldn't be an order 1 operation, okay? So in a language like Scala, you have a parallel collection. So you can turn a serial collection into a parallel collection just by sticking a .par on the end of it. And the map operation on this is parallelize. So obviously, you don't always have infinite parallel hardware. You might only have 8 cores on your laptop or whatever. But it will automatically parallelize that map operation over all the cores on your laptop. Okay? So the difference in your code here is only in your initial collection. Is this initial collection parallel or not? Okay, and after that, all of your operations are trivially parallelized. Now, what about folds or reductions? Okay, so what do we mean by reduce? Well, by reduce, we mean combine all of the values using this operation. Okay, so here I just mean combine all the values using plus. Okay, now in general, a sequential fold couldn't be parallelized. However, this particular fold definitely can be parallelized. So why? Well, because the values, the integers here, form a monoid under the folding operation addition.
Couldn't it be that the communication time between the different cores actually makes it slow?
It could. It could. And so they're relatively intelligent about how they do this. So for this particular example, it would almost certainly be slower to use the parallel version, right? But if this was a big data set with tens of thousands of elements, then it would definitely be faster. Yeah. Okay, so a monoid turns out to be a very important concept in FP, which is kind of funny because in like undergraduate mathematics, you study groups and you sometimes study semi-groups, but you rarely talk about monoids. So monoids sit somewhere in between, right? They're a semi-group with an identity or a group without an inverse, depending on how you prefer to think about it. Okay, so you've just got a binary relation. It's closed and associative, so that's the really key thing. Okay, because if it's associative, then the order of combination, well, be a bit careful how I say that. It's not commutative, it's associative, right? But the order in which you do the combinations can be done in any order, and so you can tree reduce. Okay, so if you can tree reduce, so that is you put all of the values in the leaves of a tree and then you propagate up the tree pairwise. Okay, so the height of the tree is log n, right? So on infinite parallel hardware, any reduction operation can go from order n to order log n. So your maps go from order n to order 1, your reductions go from order n to order log n, okay? And this can all be done for free when you kind of set up your problem in this way, right? You don't have to do anything. The collections take care of the parallelization logic for you, and kind of nothing can go wrong in the sense of all the things that often can go wrong in parallel programming, right? They just don't go wrong. So you've maybe heard of MapReduce. Well, MapReduce is just exactly this pattern. If you do a map and then you do a reduce. Okay, in fact, in Scala there's a single function to do it called fold map. Okay. But the point is, if you've got a parallel collection, this will happen in parallel in order log n time on infinite parallel. Okay, so again, a little statistical application. Suppose you're calculating the log likelihood of an IID model. You have some way of calculating the log likelihood contribution of one particular observation, but then you have some big collection of observations, and again we're thinking like big data here. That might be stored in a collection called X. How do we compute the log likelihood of the model? Well, we start with our big collection X, we map the log likelihood, and then we reduce with sum, because it's a log likelihood, right? So the sum of the logs is the product of the likelihoods, and we get back the log likelihood for the model. And the point is that this map reduce can be done in parallel. So if I pass in X as a serial collection, this will happen in serial, okay, in order n time. But if I pass in a parallel collection of observations, then exactly the same code, right, this is absolutely key, exactly the same code will be executed in parallel. I won't have to change anything about my code to make this happen in parallel on all available cores.
And it's returning the log likelihood as a function of the parameter theta.
Yeah, so there are kind of notational things I don't want to get in here. So you notice that here I've got 2 argument lists rather than a function with 2 arguments, and
Right.
this is all to do with currying and uncurrying, but again, it's not really relevant here, but yes, what this will give me back is a function, in fact, to evaluate the likelihood at any arbitrary theta. Right, so what's all this got to do with category theory? So like a 5-minute crash course on category theory. So a category is just a collection of objects and arrows. Okay, the arrows are usually called morphisms, but you can call them what you like. So you might think graph theory, only it's a bit more complicated than graph theory, because typically you'll have infinitely many objects, and even when you don't have infinitely many objects, you'll nearly always have infinitely many arrows, and sometimes you'll have uncountably many objects, and often you'll have uncountably many arrows, etc. So intuition from graph theory isn't necessarily very useful, but it's a good starting point. The point is that if you have 2 arrows, so you've got an arrow from x to y and another arrow from y to z, then the composition must exist, okay? So there must be an arrow from x to z. We call that the composition, and this composition must have this identity, this associative identity, yeah? So what we're saying is that it's a category if all of the compositions that could exist do exist, and all of the compositions are associative. That's what makes it a category. So you see, this is why it's a good model for computation, because if we've got a computation that takes an x to a y and another that takes a y to a z, then we know we can compute the composition that takes you from x to z, and we know that these compositions have this associativity property that we know function composition has. So this is what makes it a good model for computation. But in some sense, this is all category theory. I mean, I wish this is all category theory, because it's like utterly mind-boggling. But that's the basics of what is a category. Okay, and you've got to have identities and things like that. So the kind of canonical examples that are most useful for thinking about in terms of functional programming is the category set, where there's an object for every set, and the morphisms are functions between sets. Okay, so again, you can see that this is a mind-bogglingly huge category. Okay, you've got all possible sets as objects and all possible functions between sets as the morphisms. Okay, so it's huge. Okay, you couldn't possibly enumerate it, but it's a category. Okay, because functions are composable and have identities, and function composition is associative. The important thing to get your head around is that in category theory, the objects are atomic, right? So it's not like you're allowed to look inside an object and say, okay, so what is in this set? What elements are in this set? You can't do that in category theory, right? You can sometimes learn about what's in them by studying the morphisms. That's a different matter. But the objects are atomic, okay? And that's the sense in which category theory is point-free. And again, this is a different style of programming. Instead of thinking about elements, you think about functions, okay? Functions compose, and you don't have to worry about elements. This is very much, again, in the style of functional programming. So in FP, we just take the obvious kind of version of this, where our objects represent types. So if you think about programming, you might have doubles, you might have ints, you might have strings, okay? They're our objects, and the morphisms are functions from one type to another. Okay? So in Haskell, it's called Hask, but it's essentially just set. It's just the programming language version of set. Okay. So a functor maps one category to another. Okay. Now I said that a functor was just a data structure that supported map, and that's exactly right. But this is the sort of category theory way of thinking about it. You map your objects from C to D, and you map your morphisms in C to D in a consistent way. Okay. So what do I mean by a consistent way? Well, I mean, if you've got an arrow going from x to y in the source category, in the destination category, that must be an arrow from f of x to f of y. Yeah? And that is the sense in which you can map your morphism into the destination category. So that's a way of lifting your morphism, lifting your function into the functor. Okay? And there must be some self-consistency properties, so I'm not going to get into these self-consistency properties. I definitely don't have time, but I just want to focus on this one. What this one says is you must consistently map the compositions as well. So if you have an arrow that represents the composition of 2 functions in the source category, that must be the arrow corresponding to the composition of those two images in the destination category. Okay,
It's basically like a homomorphism between groups. Right?
it is, and in the context of functional programming, it's called map fusion, and it's going to turn out to be useful. But yeah, that's pretty much exactly what it is. Okay. In programming, we're nearly always going from Hask to Hask, from the category back to itself, and so that's called an endo functor. Natural transformations, then, so this is why category theory gets hard, because the abstraction just keeps going up and up and up. So we started with a category, then we had a mapping from one category to another category that we called a functor. Now we're going to map from one functor to another functor, and that's going to be called a natural transformation. And again, there are some consistency properties that are required. I'm just going to gloss over this because the only reason I'm actually introducing it is because it's technically required in order to define a monad, but we already sort of know what a monad is, so we're going to gloss over the details. So basically, you have a way of putting something into the monad, okay, and you have a way of flattening. Okay, that's all we can do. So if we think about a collection of data points, right, we can make a list with one element from an element, right? We can do that. So that's our unit. And if we've got a list of lists, we can flatten it down to a list. So that's our multiplication. Okay. So that's all it says. And there are these consistency requirements, but they're just the obvious things. So it's like saying if you've got a list of lists, then there are two ways you could flatten that. You could flatten the inner list of lists first, and then the two remaining lists. Or you could flatten the outer list of lists first, and then flatten the remaining two lists, okay? And they just give you the same thing. And the identity says, well, there are two different ways you could start with a tx and get a t of x, right? So if you've got a list, you could just wrap the whole thing in another list and make that a list of one element, which is itself a list. Or you could wrap each of the individual elements in a list, okay? And then if you flatten back, you get to the same thing again, okay? So these are just very obvious self-consistency requirements that you're bound to want to have.
Are there any actual sort of results from category theory that you rely on here, or is it just the definitions and language that you find convenient?
It's the definitions and language, mainly. However, these self-consistency properties, as we'll see, actually turn out to have practical advantages. Okay, so there's a reason why you want these properties, there's a reason why you'd want to check these properties, because you can then exploit those properties in your code, as we'll see one trivial example of this in a second. So what I said is that we can compose these monadic functions by chaining them together with flat map. Okay, the way category theorists talk about this is they talk about forming the Kleisli category for the monad, where composition in the Kleisli category is this flat map operation that we've talked about. Okay, so again, the details aren't important. They're all just kind of formal ways of talking about these very natural things that you would want to do in your programming anyway. Okay. But another wonderful thing about category theory is almost every concept in category theory has a dual. Okay? And the dual is typically formed by taking the original things and then turning all of the arrows around. Okay? So a comonad is basically like a monad, except the arrows are turned around. So for a monad, we could put something into it, and we could apply a function that took a plain value to a monadic value. A comonad, you can always take a value out of it, okay? And you can apply a function that takes a monad to a plain value. Sorry, a comonadic value to a plain value, okay? And there are the corresponding laws. And again, they're just very simple self-consistency requirements that you totally expect to have. So co-unit is sometimes called extract because it's a way of taking a value out of the comonadic value. And co-multiplication is sometimes called duplicate because it's basically, if we think in terms of a list, you can sort of make a comonad out of a non-empty list. It would be, say, I can take a list and I can make a list of lists. Okay, but you have to make the list of lists in a very special way to make these self-consistency laws satisfied. Okay, and we'll see examples of this in a second. Okay, so there are all of these concepts that we can use. There are all of these self-consistency properties. We do sometimes use the theorems, but actually it's mainly just the structures, the language, the self-consistency properties that we rely on in functional programming. Okay, so if you're into big data, you've probably heard of this software library called Apache Spark. So what is Apache Spark? Well, it's a library for doing big data analytics in the cloud, which sounds very trendy. But actually, when you look into what it provides you, what it gives you is something called an RDD, a resilient distributed data set. What is that?
Say again?
Resilient distributed data set. What is it? It's just a lazy distributed parallel monadic collection. Okay, so it's just a collection where you can shove lots of data. Okay, but the idea is it could be like terabytes of data distributed across a huge cluster. Okay, but it has methods like map and flat map and reduce that you can call on it, and all of these operations are not only parallelized but they're distributed so they can run across the entire cluster. Okay, however, the way you program it is exactly the way you program any other collection in Scala, right? You just assume you've got this collection of values, you can transform it using map operations, using flat map operations, you can compute summaries using reduce, okay? You just program it with exactly the same code. So not even just like similar code, but exactly the same code that we'd use on any trivial size collection that, you know, easily fits in memory on your laptop, okay? And that's the beauty of it. Okay, so there's lots of clever stuff going on under the hood to kind of do this distribution of your data, make sure everything is kept in sync across these parallel nodes on your cluster. And it's the resilient means that actually even if one node goes down, you can like bring up another node and re-replicate the data onto that other node and just do exactly the computation that needs to be redone to recover where you're up to, etc. Okay, so there's all kinds of clever stuff going on under the hood. But as far as you're concerned, it's just a collection. Right? You're just doing your map operations, doing your flat maps, doing your reducers, computing all of the things you want to compute. That's basically the whole idea behind it. Now, one thing that makes it slightly different from regular Scala collections is that it's lazy. So what do we mean by lazy? Well, in regular Scala, if you had a collection and you mapped a function over it, you'd immediately get back a new collection. Then you mapped another function over it, you'd immediately get back another collection, well, as soon as it's computed. Then you could reduce it to compute a value, okay? Then you get your value of type V. That's all fine. However, we can use that second functor law that I said we were going to call map fusion to instead compose the functions f and g and just map the composition of f and g, okay? And again, with a regular Scala collection, you would have replaced a sequence of two maps by one map. So you'd have actually got rid of an intermediate collection. So in regular Scala, this would typically execute faster than the first version, yeah? Because you've got rid of an intermediate collection, so that's going to be more efficient. Interestingly, so there are two things to say about that. So one is, we've actually used that functor law to rewrite our code in a completely automatic way, okay? So all of those self-consistency requirements actually correspond to ways that your code could be transformed without changing its meaning. But in most cases, one way will be faster and more efficient than the other, okay? So we've actually immediately got a bunch of transformations we can automatically apply to our code to make it faster and more efficient, which is kind of interesting, okay? However, Spark is lazy in the sense that you do all of these things and you get back another RDD, but nothing actually happens until you call a reduction operation, okay? So you can say RDD map F map G, and it says, okay, here is that object, but it hasn't actually done any computation. It's just stored the fact that when you do a computation, it needs to map F and it needs to map G. Then when you actually ask for a value, I say, okay, reduce, give me the value. It can then look at the entire computational pipeline and think about what optimizations it can do. So one of the things it will think is, actually, you've got two maps in a row there, I should fuse those maps. Okay, so that's one thing it can do. But it also can do a lot of other stuff to do with minimizing data shuffling. So if you think about all of the operations you could do on your data that's distributed across this big cluster in the cloud, the main thing that's going to slow you down is having to shuffle data around from one node to another. Okay, so what the Spark library does is it looks at your entire computational pipeline and looks at how it can optimize that entire computational pipeline in order to minimize the amount of data shuffling that happens, so that you can execute your query, as they like to call it, in the minimal time. Okay, so that's a potential benefit of laziness here. Okay, you can argue about whether laziness is good or bad in the context of statistical computing, but there are definitely several cases where that's a useful thing. Okay, so Spark was invented for big data, okay, and that makes sense. But if you think about it, you can use it for big computation as well by distributing your computation. Okay? So, for example, the trivial example would be something like a particle filter. You might be just particle filtering a very short time series, but if you've got hundreds of thousands of particles, you can distribute those hundreds of thousands of particles across a cluster, and you can do your map and filtering operations on those hundreds of thousands of particles in parallel. Yeah? So it's not really just about big data, it's also about big computation as well. Okay? So if you just want to be able to exploit parallel computing hardware, thinking in terms of these parallel monadic collections, and in particular these distributed monadic collections, is a good way of thinking about how to distribute your computation in a very kind of easy and convenient way that's very little effort over and above just writing your code normally. Okay, so I'm running out of time, so I'm going to skip over things a little bit. When we translate all of these things into functional programming, a monoid just has a combine operation, a functor just has a map operation, a monad, in functional programming we often think in terms of pure and flat map, so pure puts a value into the monad, flat map allows you to apply this monadic function and get back another monad, and for comonad it's the other way around, so extract will get a value out of a comonad, and co-flat map will allow you to apply a function that goes from the comonad to a value and get back a new comonad. And the way we think about this is we think of this as being a local computation on the data structure, and co-flat map extends that local computation to a global computation, okay, that's applied all over the data structure. I've got an example of that in a second. Okay, so suppose we're interested in doing ABC, okay, so hopefully everybody's vaguely familiar with what ABC is. Basically, you simulate some synthetic data, you compare it to your real data, and if you've got a good match, then you must have picked some good parameters. Yeah? So you pick some parameters, you then simulate some synthetic data, and you compare the distance between one and the other. But if you think about what that means in terms of programming, it's trivial, right? You have a summary statistic for your real data, then you're going to take a collection of parameters that might be a parallel collection, you're going to map the composition, so we may as well fuse the maps, the composition of simulating the synthetic data and summarizing it. So again, this map fusion could be really crucial because your simulated model might be huge, right? You might simulate a massive amount of data, but then you might just compute a handful of summary statistics from it. So you absolutely don't want to store all of the output from your simulation model. You just want to summarize it as you're simulating. Okay, so you want to do this map fusion where you simulate your simulated data and the summary statistics, and then you're just going to keep the ones that are not too far away from what you hoped. Yeah, so this is just a way of expressing approximate Bayesian computation as just a map and a filter. Okay, and again, completely parallelism agnostic. This code does not care whether or not your collection is parallel. And you do the same with particle filtering, right? So what you do is you write a function that is parallel agnostic that takes a collection of particles in an observation and gives you a new set of particles, right? That's the key to particle filtering. That's one step of the particle filter. And then you just fold it over your data set, okay? So fold left means start at the left-hand end with the accumulator set to an initial value, and then use your update function to sequentially work out new values and return the value that you get at the end of your collection. Okay, so a particle filter just becomes a sequential fold over a set of observations. Interestingly, the only thing you care about is you have some way of folding this, and so it's trivial to generalize this. So you're not just folding over a sequence of data structures, but you could fold over a tree, for example. Okay, it's an interesting paper out not long ago about doing sequential Monte Carlo on trees, but again, it's just turning this fold left into a fold, and then it's exactly the same procedure. Okay, so again, there's essentially no code changing in doing this over sequences or over trees. It's the same basic structure. Okay, so I have a PhD student, Johnny Law, who's looked at doing this sort of thing with nonlinear continuous time state space models with regularly spaced observations. So you can start off with a stochastic process, you can add an observation model, but then you can just add in seasonal components, etc. So you're sort of composing together your model in bits, and then you can apply that particle filter to infinite streams of data. So if if you've got some streaming data architecture, you can just drop this particle filter into that streaming data architecture and can have an online particle filter running inside your data stream. And you've got more conventional sort of state space modeling code as well. Okay, so what about comonads? Very, very quickly. They're a way of extending local computations to global computations. So how can I explain this? The simplest way to explain it is we think about having an infinite data stream. And again, in functional programming languages, because they can have lazy semantics, there's actually no problem working with infinite data structures at all. Obviously, you can't do all of the computation on them, but if you think about an infinite data stream, you just do one observation at a time. That's fine. It's no big deal. And you have some termination criterion, so you don't go on forever. So as long as you're careful, there's no problem working with infinite data structures in FP, and it's often very convenient to do so. So we've got our infinite data stream, okay? We're going to think of it as a comonad, okay? So what we're going to do is we're going to define, say, a linear filter. So hopefully, again, everyone knows what a linear filter is. You just wait. You have a sliding window where you take some linear combination of a window, you compute basically a weighted average of a set of values, then you slide your window along one, apply it again, slide your window along one, apply it again. So how would you do that, thinking of the stream as a comonad? You'd write a function that works out the very first smooth value, okay? So it's going to take in a stream and some weights, and it's going to multiply the weights and the values together and then add them up, okay? So that filter is a local computation. It just looks at the local neighborhood structure at the head of the stream, and it computes the linearly filtered value for the very first point in the stream. And then coflatmap is going to apply that to the entire stream. Okay? So that's how you think about comonads and coflatmap. You've got a computation that requires some local structure to compute, right? You need to know about neighboring values, say, but you can write a function that does a local computation on those neighboring values and gives you one value back, and then coflatmap will extend that to the entire thing. Okay? So that's how you'd apply a linear filter to a stream. But that's essentially the same as applying a filter to an image or integrating a PDE. Okay? So suppose we want to apply some simple linear filter to an image, say to do some Gaussian blurring of an image or something like that. Okay? Well, we need to know what extract means. Extract gives you a value back. Well, which value does it give you back? Well, so you need to make your type pointed, okay? So you need to add a cursor to your image type saying where you are in the image right now, and then extract will return where you are now. You can also add some navigation functions like up and down and left and right to move the cursor. So you get the same image but with the cursor moved by one position, okay? So then you can write your filter as, okay, well, I want to write 2 times the current value plus 1 times the value up, down, left and right, okay? So I'm taking a simple weighted average of up, down, left and right, okay? So that's my filter, and then I apply that to the image with coflatmap. And if I want to, say, do that again and again and again to get more and more smoothed images, well, I can create an infinite stream of smoothed images just by starting with an initial image and repeatedly applying this filter using coflatmap. Okay, so then I get an infinite stream of smoothed images, so I can see which one I like the look of. Okay, so but the point is, okay, the crucial point is that none of this code cares about whether it's parallel or serial. So if I back this image type with a parallel collection, all of this will happen in parallel. So I'll be doing all of my image analysis in parallel. And similarly with Gibbs sampling, say an icing model. Okay, so again, I'm kind of hoping people have heard of an icing model. It's just a binary image where there's a local neighborhood dependency, pretty much of the type I've just described. Okay, so up, down, left, and right. So the way you simulate a new pixel, okay, using the Gibbs sampling algorithm, is you look at the neighbors and you use the values of the neighbors to determine the probability that you sample a black or a white pixel. Okay, so that's your Gibbs kernel. You want to extend that local computation to the entire image. You've got to be a little bit careful how you do that, because conceptually, you only preserve detailed balance if you apply your Gibbs kernel sequentially, okay, 1 pixel at a time. Whereas the semantics of coflatmap, however it's implemented, are in parallel. Yeah. So if you were just to coflatmap that Gibbs kernel over your image, actually you'd end up with the wrong dynamics, because you'd kind of violate detailed balance. However, it's trivial to see that if you kind of colour it, imagine colouring it black and white like a chessboard, the black squares would be conditionally independent given the white squares and vice versa. So what you can do is just define a new kernel, odd kernel, and even kernel, which kind of leaves one alone and only updates if it's, say, the odd kernel only updates if it's odd and the even if it's even, okay? Otherwise it just leaves it alone. So then that kernel you can apply without violating detail balance. So again, we can compute an infinite stream of MCMC samples by co-flat mapping first the odd kernel, and then when we've finished, we co-flat map the even kernel, and that will then give us a complete update. We'll have an irreducible chain that preserves detail balance. So this will then give us an infinite stream of MCMC iterates. Okay, and again, if your image is backed by a parallel data structure, this whole MCMC algorithm will be executed in parallel without any effort. Okay, and there are loads of these concepts that crop up everywhere. So, so folds are more formally called catamorphisms. These unfolds or iterates are actually called anamorphisms. If you kind of generate and fold at the same time, that's sometimes called a refold, but again, mathematicians would call this a hylomorphism. So I have an example there, but maybe in kind of the context of frequentist statistics, you often optimize things with iterative algorithms, okay? Optimizing something with an iterative algorithm is a hylomorphism, yeah? You're generating an infinite sequence of values, hopefully each value getting better than the rest, but then separately you have a termination criterion that you're applying that's consuming these iterative values and then deciding when to stop. Yeah? So you don't actually have to generate the entire infinite trajectory of iterations and store them and then decide when to stop. Right? You can generate and consume. Okay? And if you were writing this algorithm even in an imperative way, that's what you do. Right? You just keep maybe the two previous values and compare them to decide whether to stop. But a hylomorphism allows you to think about that separately. Think of the generation of your iterates as being a completely separate process from the termination criterion, but still being able to apply them together in an efficient way. So that's a well, I would call a refold, but again, mathematicians would call a hylomorphism. Okay. So, and again, there are libraries to support you thinking this way and working this way in functional programming languages. So I don't really have time to talk about modeling, but basically, probabilistic programming languages are based on building probabilistic structures, which you can think of in terms of probability monads, okay? And these are by definition very compositional things that you want to do, okay? So you can compose random variables together using flat map, okay? So that's where we're using the monadic structure of probability distributions. We can then use that to build very complex probability models from very simple probability models, and all of the structure is there, right? I talked about these 4 comprehensions in Scala, where you just kind of take things out of monadic values, and actually this just compiles down to a bunch of flat maps, but it looks very much like imperative code, but here it looks very much like a probabilistic programming language that you might write in Bugs or Jags or Stan or something, yeah? It's just this has a Gaussian distribution, this has a gamma distribution, right? I haven't written this as some sort of language inside the functional programming language. All functional programming languages allow you to write things like this, you know, by default. Yeah, you don't have to build all of that additional machinery. It's all there ready, waiting for you to use. Okay, I was going to say something about what exactly a probability monad is, but I definitely don't have time for this. But it's fascinating actually, because everybody hates measure theory. Okay, so so you can define exactly what a probability monad is in terms of measure theory, but it turns out that that's not very nice, because the category of measures isn't Cartesian closed, and so in probabilistic programming languages we like to be able to define probability distributions on functions from one space to another, as well as just on spaces. And of course in measure theory that gets very hard very quickly, because you know, it's a bit delicate. You know, even just defining probability measures on functions from R to R, it gets very tricky very quickly. So lots of people are thinking about different ways of thinking about the foundations of probability that's somehow more composable. So that's kind of interesting as well. And then, yeah, and we can use that semantics to allow us to think about how to propagate uncertainty through computational pipelines, and that has applications for uncertainty quantification. And then ultimately, what I want to do is kind of build much more flexible and scalable tools for Bayesian hierarchical modeling, where I can build models in a nice scalable hierarchical way. I can apply inference algorithms in a very composable, scalable way, where I can run HMC on this bit of the model and do a Gibbs sampler on this other bit of the model, where maybe it's discrete and I can't do HMC, and actually to do this very simply and easily in a scalable way. Okay, so wrapping up then, basically we're not the first people to think about how to do computation and what computation means and good ways to think about it. Yeah? Mathematicians, computer scientists have been thinking about this for decades, and I think there's just lots we can learn from what they have learned about how to think about computation in a good way. And I think it leads to just better ways of thinking about computation, perhaps even changes the way you think about algorithms, and the way you think about scalability. But on a more practical level, it just leads to kind of better, neater code and algorithms that parallelize more easily. So even if you only care about the kind of hard benefits, I think there are some hard benefits there as well. Okay, so yeah, so that was a real whirlwind tour, probably a bit mind-blowing, but I just leave you with a few references there in case there are any bits of it you fancy picking up on later. Thank you.
Well, I'm not sure I've been to a talk. There are so many words I've never come across. Well, would you have us teaching Scala instead of art to our undergraduates, or would you say, oh, is that a little bit extreme?
Yeah, I think that is a little bit extreme. So I do teach a course on Scala for statistical computing, but not to our undergraduates. In some ways, I think it probably is. It's just a little bit easier because everybody in statistics uses R. This is the thing. And so there are pros and cons with that. So I remember the days before everybody was using R, and that had problems as well. But now everybody uses R. Everybody's using this language that actually is a pretty terrible language for statistical computing, right? It's slow, it's quirky, it's just not a good language. So it's great that everybody uses the same language. It's just a terrible language for everybody to use. But how do you get away from that problem, right? There are like thousands of R packages on CRAN that implement every method, right? So in Scala, right, you've got all the tools there. You've got nice scientific computing libraries, right? But you don't have an R package that implements your latest method, where there probably is an R package that implements your latest method, and that's a problem. So I think for undergraduates, it probably at the moment, sadly, does make sense to teach them R first. But I think in a kind of later level statistical computing course, this probably makes a lot of sense. So actually, I've just agreed to take over the statistical computing course. And so I'm wondering if I should do any Scala, but I think I'm probably not very much. So I'll probably mainly do R, but maybe give a little taste of Scala on the last day or something like that. I'll see.
So we had two questions. One is following up on Richard's, which is on a more general level. Can you envisage a course that is a bit more formal and starts with rudimentary category theory and then moving on to how to think about programming? Maybe not necessarily in R, but programming in general, statistical computing.
So I totally could see that. That isn't actually the way I do it. So I say I teach this Scala course. What I actually do is I start off teaching the practical stuff, like how to use collections in parallel and solve statistical computing. And then I go into the category theory once there's the motivation there. I'm not sure if you just started with category theory, people would just think...
interlaces things, maybe.
Yeah, exactly. So maybe blending them together somehow. Yeah,
Because if I understand from Richard's question during your talk, it's more of a formalism and a framework for thinking, rather than necessarily that you need to refer to theorem X.
Precisely.
And
precisely.
Maybe another question. Kantorovich. So in what sense the Kantorovich formalism? That's something I couldn't immediately see. So does it have to do something with coupling and with, you mentioned joints and marginals, or?
Yeah. So the whole problem is that
Kantorovich monad, yes.
Yeah, so there are two approaches to getting away from regular measure theory. So the probabilistic programming people are going this quasi-Borel spaces route, which is basically just like measure theory, but just being a little bit careful to work with measures that behave nicely. So that if you can define measures on R, then you can easily define measures on functions from R to R and things like that. Yeah. So it's just a slightly more compositional tweak on regular measure theory. But the Kantorovich monad basically just starts with complete metric spaces and just defines what probability is in a completely different way using kind of maps. Okay, so basically it defines measurable functions rather than measurable spaces effectively. So it doesn't do away with measure theory completely. It would be nice if it did, but it's much less tightly linked to measure theory. So I'm not the right person to explain this because I barely understand this stuff. But it's interesting, and it's a rather different way of kind of coming up with a foundation for probability. But again, the main motivation is that it's much more composable. You define everything on a Cartesian closed category, and so everything kind of links together nicely. So it's quite different from the quasi-Borel space approach. Okay, thank you.